Hey there! Have you ever wondered if a ceiling fan can be turned into a wind turbine? I have one left over, so let's find out. There are a couple of reasons why I think ceiling fan is interesting to use. Because it has a large, low RPM stator, no gears or belts, it has a strong shaft and strong ball bearings, there are no brushes, better wings can be attached easily, and it can often be found for free in the trash. Okay, first thing to do is to get it open and to remove all the stuff that we do not need. It starts with 3 wires. You will probably need none of them. These 3 go through the motor's core into the control box on the other side. All that stuff in the control box is useless to this project. So take it all out. First we had 3 wires on the one side. Now we're left with 4 different ones on the other side.
See how well this thing spins. It looks like a solid base for a wind turbine. But the main reason why this project is a bad idea is that this is an induction motor. It will not generate electricity when you spin it. Therefore, we have to add magnets. Yeah, I thought that would be easy. So next, the core of the motor needs to be opened. Here you see how I got mine open. Yours may be different.
Getting the motor to open was quite difficult, but we found this handy trick. Connect one side to a wooden plank with a hole in it, then you can easily kick out the other part without causing damage. Alright, tada! It's open. This half contains the rotating part of the induction motor. We don't need this part, because instead we're going to place magnets in there. And here's our first view of the stator and its coils. Pretty impressive and complicated. This is the stationary part of the motor. It contains the coils and a really weird shaped iron stator. As a motor, it can run at 3 speeds and in 2 directions. That's why it's so complicated. We are going to make it simple by only using the large coils. Now, how does this weird stator work? I will be ignoring the inner coils. When an electric current is running through the copper wire, the 2 iron parts inside of one coil both turn into a magnetic north or south pole, depending on the direction of the current. The direction of the coil's wire is alternating, and the electric current is alternating as well, resulting in an alternating pattern of poles. We are turning this induction motor into a generator. Therefore, we need as many magnets as there are coils. At first, we used cheap magnets, just to see if this weird stator would work at all. We have 4 wires. The 2 for the inner coils we don't use. Be sure that these ends don't touch, as that will be like having a strong magnetic brake on your generator. The 2 wires coming from the large coils will deliver AC, alternating current. Turning the generator slowly is already enough to light some LEDs. But be careful, because turning it any faster will kill the LEDs. Okay, now that we know that this weird stator can produce electricity, we should make a better rotor, because these loose magnets are weak and the air gap is huge. And how to improve the stator? The inner coils may be a magnetic drag. I'm not sure, but I do love to remove the unnecessary. And we soldered a thicker copper wire to the coil's ends, better than the flimsy original wire. This then is the improved generator. It now contains strong magnets and the air gap is reduced. But actually, There still are many ways to improve on this, as I will explain at the end of this video. The generator spins well, not too much magnetic cogging, and look what happens when you make a shortcut. As soon as the two wires touch, the rotor stops spinning. That's a good sign. Current is flowing, Lenz's law at work. The conversion from induction motor to generator has succeeded. It may not be the best generator ever, but with a little spin, this incandescent lamp starts to glow. Putting the two shells together again gives the generator body more strength. It is time to put some wings on it. I have some old RC helicopter blades that may work. A real airfoil and weatherproof. With the helicopter blades attached, it really starts to look like a wind turbine. Though this experiment is far from over. Because don't expect to charge your phone with this electricity. Using this electricity straight from the source will kill your phone. A phone needs a steady 5 volts DC, while this generator produces unsteady AC current. The complete opposite of what you want. Now, how can we convert this useless, almost random electricity into a useful, steady 5, 12 or 24 volts DC current? First we need to know what we have. We know we have an AC current. Measuring the AC without a load gives up to about 50 volts. That's very useful. With the load attached, the voltage will be lower. First thing to do is to connect a full bridge rectifier, which contains 4 diodes, transforming the AC into pulsed DC. When connecting a small LED panel to it and turning the rotor very slowly, you can see the pulsing DC current. Spinning the rotor faster will produce too high a voltage and kill the LEDs. So don't do that. Placing a capacitor on the DC output of the rectifier is like placing a large room for the electrons to gather in, resulting in a more steady flow towards the LEDs. As you can see, it's more steady, but the voltage level is still all over the scale. In between the DC output of the rectifier and the LEDs, we placed a DC to DC converter. It takes in any voltage up to about 30 volts and brings it to a level you have selected. Here we set it to output almost 3 volts. The DC output is now steady and pretty safe to use. This DC to DC converter gives you a couple of options: to set the output voltage, to limit the output current, and I think a way to set a minimum voltage input. Anything USB needs a steady 5 volts DC. That and the other levels can be set with a small screwdriver. Although the electric system works, we are not done yet. There are many things I do not like about the construction so far. There's a hole in the center of the soft iron that reduces the magnetic force. The air gap is still too large. The copper magnet wire is very thin, giving a lot of resistance. The magnet wire is wound so that it doesn't touch the sides of the iron core, losing magnetic touch. The magnets are glued on wood instead of iron. All these issues reduce the potential output of this generator. Question is, what can we fix, and is it worth doing that? And if you have something useful to add, please write it down in the comments below. Here is where the unwanted hole in the iron is. It's probably only there to give access to the machine that wounds the inner coils. We can fill the holes with laminated soft iron, and by doing so get a stronger magnetic force
to work on the copper magnet wire. This is soft iron laminate. A good source of it are old transformers, like this one. We glued the iron in the stator. It's messy, but now the iron can't move towards the magnets. This thin wire and how it's not in touch with all sides of the iron core. Look at this space. Best would be to rewire the stator tight with thicker wire, but that's expensive and a lot of work. I'm not going to do that. So, after adding the extra iron, we've put it back together. This time in a more compact way. This bolt locks the axle and this tube protects the wire. The extra soft iron improved the magnetic force and the power output a bit. Slowly rotating the generator with just one finger turns all the LEDs on. Now, for the next part, I can use some help. Some good suggestions in the comments, please. This is about my first time working with electronics. I know how to improve the generator, but the electronics, not so. I think my collection of parts is not efficient and not safe when the generator turns too fast. But here's what I got. The AC from the generator goes into the full bridge rectifier. On the DC output of the rectifier is a capacitor that can handle up to 50 volts. If the voltage goes higher than 50, there's a problem. From the capacitor, the current goes through a linear voltage regulator, which lets no higher than 24 volts through, which is near the maximum the DC to DC converter can handle as input. When the voltage is higher than 24, the linear voltage regulator will waste that power into heat. And when the input is too much of everything, it shuts itself down for safety. Then a simple DC to DC converter that shows the input voltage and can efficiently convert anything between 6 to 24 volts into a steady and safe to use 5 volts DC. We now spin the generator too fast, on purpose, to show how the linear voltage regulator will shut itself down. It's not broken, it just needs to cool down. Next and last, in the USB output of the DC to DC converter is a USB power meter with a small LED light in it. You can see how the output is a steady 5 volts, if there's enough input power. Time for a conclusion. I of course wanted to end this video standing outside next to a finished wind turbine, but I decided not to continue with this generator, because the power output is very disappointing, and I understand why. I basically created a very poor quality generator. So yes, a ceiling fan can be turned into a wind turbine, but I don't recommend it, even if you do a better job than I did, because there are better alternatives. Better alternative number 1 is to simply use a brushless motor that contains magnets. Here's some examples. One from a quadcopter, one from an e-bike, and one from a hoverboard. Better alternative number 2 is to build a generator from scratch. This is more fun and a lot of work, but the result can be better than building upon a poor quality ceiling fan. I'm looking forward to read your comments and hope that some of you can make a better version ceiling fan generator, having learned from my version 1. Alright, have a good day making something. See ya.